Welcome to the online video lecture series for college algebra, Wayland Baptist University. I'm Dr. Scott Franklin. I'll be taking you through these lectures. We have now reached the point where we're going to cover our last chapter of the term. This chapter introduces a new set of mathematical objects known as sequences and series, both of which have a large number of different applications that show up in a vast variety of fields. Before we get to the point that we can start talking about those applications, we need to lay down a set of definitions and notations that we will use and basically just discuss what in the world sequences and series actually are. So let's get started with that. So definitions and notations. Let me begin by talking about one of the most common and well-known sequences in mathematics. Comes up in a lot of different applications and has even shown its head in some popular culture, like I think a number of movies recently have talked about the Fibonacci sequence, movies like The Da Vinci Code or National Treasure. Anyways, what the Fibonacci sequence actually is just a list of numbers that follow a particular pattern. In this case, the pattern that makes it the Fibonacci sequence is the fact that each term after the first two is the sum of its previous two terms. So if we start with 1 and 1, the next term would be 2. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13. 8 plus 13 would be 21 as the next term in the sequence. 13 plus 21 gives us 34. And 21 plus 34 gives us 55. It's even interesting that in some natural occurring phenomena we see the Fibonacci, like if you look at some of the patterns, as in the sunflower seeds in a sunflower plant, or the hexagonal pattern on the outside of a pineapple. There's a relationship to the Fibonacci sequence. If you're curious about those, you ought to take the time to go out and just do a Google of a Fibonacci, and you'll find a wealth of information online. So what is a sequence then? What do we mean by a sequence if I'm calling this a Fibonacci sequence? Well, basically, if I'm going to talk about an infinite sequence, all I mean by that terminology is that it's an ordered list of numbers. Okay? It's just a list. An infinite list goes on forever. Now, formally, in mathematics, we would define it as a function whose domain is the set of positive integers or natural numbers, meaning that this would be like the first element, or I might call it f of 1, and this would be f of 2, f of 3. It's a function that you only plug in the natural numbers into, and that tells you which item in the list it is. But all you really need to think about of a sequence is just a list of numbers. So the notation that we will write for a general sequence is something like this. The terms of a sequence would be written as subscript notation. That is a sub 1, comma a sub 2, meaning that a sub 1 is the first element of the sequence, a sub 2 is the second element of the sequence, a sub 3 third, so forth, right? And a sub n would be the nth term, meaning it's some function of n, but that tells you that it is somewhere along in that list where that place in the list that it is the value n. Now a finite sequence would be a list of numbers that has some total number of elements in it. Okay, meaning that it stops somewhere. It doesn't do this, meaning the dot 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 at the end isn't there. It doesn't say go on forever repeating the same pattern. So here's an example of a finite sequence where you're asked to find the next three values. Now what you will always see in these examples are a pattern established that you can readily identify what the next few terms in the sequence would be. So 1, 2, 3, 4, 5, 6, 7, 8 are the next terms in that sequence. That's a piece of cake. Now this one may be a little bit more challenging, but it's not too bad. What we see is a fractional pattern here: 1, 1/2, 1/4, 1/8, 1/16. Clearly the numerator is staying 1, and what's happening to the denominator in each case? It's doubling, right? So 2, 4, 8, 16. The next one would be 32. It'd be 1 over 64 and 1 over 128. Alright, let's try the next one. We got 2, 3, 5, 9, 17, 33. Can you identify what's happening to get from one term to the next. Well, here's what I see, and you may see something slightly different, but if it works, then we should get the same answer. I'm adding 1 here, I'm adding 2 here, I'm adding 4 here, I'm adding 8 here, right? 1, there's 2, 4, 8. To get from 17 to 33 to be 16. So what if I added the next, right? I'm adding a double of what's there before. So we can now double 16, and that gives us 32. So if I add 32 to 33, that's 65. And then we're going to take and double 32, so I'm going to add 64. 64 added to 65 is 129. And then if we take double the 64, add that, we get 128. So 128 plus 129 is 257. Now that one's harder, right? Are they always going to be that hard? Well, there is a better way than to identify what the terms of a sequence are instead of relying on a reader to determine that pattern. So generally we're not going to get anything this difficult to list out the next terms of the sequence, although it's a nice little brain puzzler. A better way to do that is to have a formula for the nth term. Okay? So say for example we have a sub n is equal to 3n plus 4. Where n is what term you are in the sequence. So first would mean n equals 1. So if I'm asked to find the first 4 terms of the sequence, I find a sub 1 by plugging in 1 for n. Notice how this is just like a function where I'm plugging in the number for n. It's just a different notation. It's my sequence notation. The second term of the sequence would be a sub 2. So 3 times 2 plus 4 would be 6 plus 4, which is 10. A sub 3 would be 3 times 3 plus 4, which is 9 plus 4, or 13. And 3 times 4 plus 4 would be 12 plus 4, which is 16. So these are the first 4 terms of the sequence: 7, 10, 13, 16, so on. There you go. Let's do the next one. Again, finding the first 4 terms. So a sub 1 would be negative 1 to the first power over 3 to the first power minus 1, or negative 1 to the first is negative 1 over 3 minus 1, which is 1/2, so negative 1/2. A sub 2 would be negative 1 to the second power over 3 squared minus 1, which is a positive 1 over 9 minus 1, which is 8. For a sub 3, we would have negative 1 to the third power over 3 to the third minus 1. Negative 1 to the third is negative 1 times itself 3 times. That's an odd number of negatives, so I'm going to get a negative 1 out of it. And then 3 to the third is 27. Minus 1 is 26. So negative 1 over 26. And then a sub 4 would be negative 1 to the fourth over 3 to the fourth minus 1. That's a positive 1 because an even number of negatives is positive. 1 times 1 times 1 times 1 is 1. 3 to the fourth is 81. Minus 1 is 80. So there are your first 4 terms in that sequence. So that would have been a hard pattern to establish by eye, but the formula gives us a fairly quick way of identifying the next term in the sequence. Now, if n is a positive integer, the notation n with an exclamation point after it is something we use in mathematics called the factorial, or read as n factorial. It doesn't just mean n with excitement, it's actually a mathematical function, right? The definition of that is that it's the product of all integers from n down to 1. Now, the reason I introduced this is that a lot of sequences that we discuss will have this notation show up in there, so you need to know what that means, right? So n factorial means start at n and then count down one number at a time until you get to 1 and multiply the result. And by definition, and for no other reason that I can explain at this level of mathematics, we are going to declare that 0 factorial, which doesn't fit this definition because we only count down to 1, not to 0. We're going to say if we ever see a 0 factorial, it means 1. Okay, again, the reason for that, there's a good strong mathematical reason, but it's beyond our level of mathematics at college algebra. So we take it as definition. 3 factorial. Can you figure that out? By definition, that would be 3 times 2 times 1, which is easily determined to be 6. 6 factorial would be 6 times 5 times 4 times 3 times 2 times 1. So that gives me, that's 30. 30 times 4 is 120. 120 times 3 is 360. 360 times 2 is 720. So that is 6 factorial. Notice how factorials cause numbers to get large very quickly. So if you were asked to find like 8 factorial, 10 factorial, or even 30 factorial, those numbers are going to be very large and usually outside the range of our calculator. So we're not going to deal with anything too large in this class, but factorials do show up in several areas of mathematics. One of the particular area that you see them is in statistics and probability. Many of you may need to take a statistics course after you finish up with college algebra, so you would expect to see the factorial operator show up in that class as well. Let's write the first 4 terms of the following sequence. We are given that a sub n is equal to 2 over n plus 1 factorial. So a sub 1 would be 2 over 1 plus 1 is 2, so 2 factorial. Now 2 factorial is 2 times 1, right? So that's 2 over 2, which is 1. So your first term in your sequence is 1. A sub 2 would be 2 over 3 factorial, or 2 over 6, which reduces to 1/3. So your second term in your sequence is 1/3. A sub 3 would be 2 over 4 factorial, because 3 plus 1 is 4. That's 2 over 4 times 3 is 12, times 2 is 24, which reduces to 1 over 12. And then a sub 4 is 2 over 5 factorial. 5 factorial is 360. Isn't it? Yes. 5 times 4 times 3 times 2 times 1. That's 20. Times 3 is 60. Times 2 is 120. Sorry, I jumped ahead. So that's 2 over 120, or 1 over 60. That's your fourth term. There you go. Now we're ready to start talking about summations, which will lead us to the definition of what's called a series. We use the Greek letter capital sigma, which looks like this giant E, for the symbol for the sum. So if I were to write this expression right here, okay, notice what I've got is I've got the Greek letter sigma, and I've got n equals 1 underneath it and 5 above it, and sitting next to it is n squared. What this means to do is to take the sequence n squared, and then starting with n equals 1 and go all the way up until n equals 5, add the result. Right? So add the sequence a sub n equals n squared, starting with n equals 1 going up to 5, and from 1 to 5. So it means plug in n equals 1 right here. You get 1 squared. Then keep going, progressing 1 n at a time. So then 2 squared, plus 3 squared, plus 4 squared. All I'm doing is plugging in values for n, and I'm going to keep going until I hit this top number up here. So that is what this notation means. So if I were to ask you to find the value of that, you would then go to your calculator or by hand add these up. 1 plus 4 plus 9 plus 16 plus 25. Okay, which turns out to be what? 5 plus 9 is 13. 5 plus 9 is 14. 14 plus 16 is 30. 30 plus 25 is 55. Okay, so that would be the value of that sequence. Or sorry, not sequence. We're going to call this a series now. Series is, by definition now, the sum of a sequence, meaning add them up. Let's find the value of this series. So I start with I as my variable and plug in I equals 1. So I have 1 squared plus 1 plus, and do the same thing again for the next number, 2 squared plus 1. All I'm doing is plugging in the next value of I into this expression. And then I keep going. 3 squared plus 1 plus 4 squared plus 1 plus 5 squared plus 1 plus 6 squared plus 1, where I'm going to stop because that's the top number. Now I'm going to evaluate each of these expressions. 1 squared is 1 plus 1 is 2 plus 2 squared is 5 plus 2 squared is 4 plus 1 is 5. I'm jumping ahead, I apologize. 3 squared is 9 plus 1 is 10. 4 squared is 16 plus 1 is 17. 5 squared is 25 plus 1 is 26. And 6 squared is 36 plus 1 is 37. We can plug them all into our calculator, or we can add them up by hand. We end up with 97 as our final answer. Alright, let's do this one. Let's try from k equals 1 to 7. Alright, so I'm going to start with k equals 1. That gives me negative 2 to the first minus 5. Plus, all I do is put a plus sign in between each one of these k's that I'm plugging in. So negative 2 to the second minus 5. Plus negative 2 to the third minus 5. Plus negative 2 to the fourth minus 5. Plus negative 2 to the fifth minus 5. Plus negative 2 to the sixth minus 5. Plus negative 2 to the seventh minus 5. I've got to stop there because 7 is the top number. So that gives me 16 minus 5. Why does that give me 16 minus 5? Because I made a mistake and thought that was a 1, didn't I? Alright, let's fix this. I've got an error, and I could go back and erase this off the video, but I'm going to do this as an example of you seeing how to catch your mistakes. This k equals 4 means I should have started right here and did not need these terms in there. Alright, so let's try that one more time. If I were to want to evaluate this series, I would start at k equals 4 and go up to k equals 7 and not include these three. Does that make sense? I hope it does. If not, certainly email your instructor with any questions that you have. Now, take this, negative 2 to the fourth. That gives you 16 minus 5. That's what this value is right here. Take negative 2 to the fifth, which is going to be negative 32, and subtract 5. Take negative 2 to the sixth, which would be a positive number because even number of negatives is positive. It should be 64. 2 to the sixth is 64 minus 5. Plus, and then negative 2 to the seventh, that is a negative 128 minus 5. So 16 minus 5 is 11. Negative 32 minus 5 is negative 37. 64 minus 5 is 59. And negative 128 minus 5 is a negative 133. Add all those up in my calculator, and I end up with 11 minus 37 plus 59 minus 133 is negative 100. This one seems a little bit tricky, but the only thing that's different about it is that it looks like there's no n inside the argument. In fact, that's true. So we're going to do everything exactly as we would if there was an n, but notice what happens. If I plug in n equals 1 into 4, what do I get? Well, since there's no n, I just get 4, right? That was for n equals 1. Now what happens if I plug in n equals 2? I also get 4, right? Because there's no n, so it doesn't change the value of it. If I do it for n equals 3, I get 4. And if I do it for n equals 4, I still get 4. And how far am I going to go? I'm going to go up till I get to 5. So this is now the 5th n. So 4 plus 4 plus 4 plus 4 plus 4 is equal to 20. So adding a constant to itself through the summation notation gives us the same number over and over again, which is just repeated addition or multiplication. So 4 times 5 would have been the same thing as 20. The last type of question that you'll be asked to answer is, can I take a series that is written out term by term and convert it into my summation notation? That is, can I take this, write my Greek letter sigma, and identify what the top and bottom here are and what the expression would be here. Now what you want to look for is the values that are separated by the plus signs. Can you see, as that expression moves from left to right, a number that's increasing by 1 each time? If you can, that's going to be what you want as your index. So let's say that I have now this number 1, 2, 3 going up to 7. That's my index. Let n go from 1 to 7. And then the inside will be whatever n is cubed. And that is equivalent to this sum. Similarly, we can see that we have an exponent moving from term to term here, because this is the same thing as 2 to the first. This is the same thing as 2 to the second. This is the same thing as 2 cubed, all the way up to 2 to the n minus 1. But here's a key. That formula's sitting right there for you. Okay, that tells you that the last term looks like this. So what I need is something like 2 to the... Now I don't want to put n minus 1 because n is the last value I'm going to plug in to that exponent. So let's use k as a different index and go from 1, right? That would be k minus 1 would be 2 to the 0, which is exactly what this denominator is, right? 2 to the 0. So I can do 2 to the k minus 1, and that is the same as this expression right here. Just check it. Plug in the k's from 1 up to n, and you get exactly this expression. Alright, that's the end of section 11.1, where we have introduced the concept of both sequences and series. In the following two sections, we're going to look at two specific types of sequences in more detail.